Hello everyone, Kotongane the Native God here. Alright, so we are going to look at another problem based on Newton's laws of motion in conjunction with work done, power and energy. Right? Let's consider this question. Question 1.1, determine the term speed. Right, so speed can be defined as the rate of change in distance. Right, so remember that the major difference between speed and velocity, right, is the fact that speed is a scalar quantity, velocity is a vector quantity, right? Hence, in their definitions, as much as they are similar, right, the major difference is here. So because speed is a scalar, we use distance here. And then if we were defining the term velocity, right, we would write it the same way, except we would replace distance with displacement. Right, so just take that into consideration. Speed refers to the rate of change in distance. Right, that was just for interest sake. 1.2, state the law of conservation of energy. Right, this we covered in the lesson where we look at work done, energy and power. Right, energy, we said that the conservation of energy states that energy cannot be created or destroyed, but can be changed from one form to another. All right. And now 1.3. Right. 1.3 reads as follows: a body with a mass of 5 kg is accelerated from 6 to 15 meters per second during a period of 20 seconds up an incline, making an angle of 25 degrees to the horizontal. The frictional force is 45 newtons. Right. Right, first things first, you draw your free body diagram. Right, in drawing your free body diagram, right, we know the normal force and the weight components. Right, those forces we always get, right, on an object that is moving up an incline. Right, so because the object is moving up an incline, it means the total force applied is applied in this direction. Hence the acceleration will be in this direction as well. Remember that the acceleration always heads in the same direction as the force being applied. Right, so the motion is in this direction, and then opposing motion, you always get the frictional force. Meaning that as far as the vector sum of forces, F net is equal to, now you look at the direction of the forces relative to the direction of acceleration. Right, the total force applied, same direction as acceleration, therefore positive. All right, now the other forces, FR and FG parallel, they are headed in a direction that is opposite, or that is opposing the direction of acceleration. So those two you take as being negative. Minus FG parallel minus frictional force. As far as the vector sum of forces, this is what they're equal to. All right, so now let's look at what else we've been given. All right, you've been given the mass. The mass is 5 kg. So we use the mass exactly as it is, because the mass we have to express in kgs anyway. So the mass of the object is 5 kgs, is accelerated from 6 to 15. So 6 meters per second is our initial. So initial velocity is 6 meters per second. Final velocity is 15 meters per second. Right. Okay. During a period of 20 seconds. So we also have time. Time is 20 seconds. Up an incline of 25 degrees. So we have theta. Theta is 25 degrees to the horizontal. The frictional force we also have So Fr is 45 newtons. Right, that is everything that we've been given. Now let's look at calculations. Determine the acceleration. Right, acceleration, that's 1.3, 1.3.1. Right, acceleration, you simply use equations of motion because we've been given the initial velocity, the final velocity, as well as the time. Right, so here I was supposed to say the final velocity is equal to 15 meters per second. So using equations of motion, acceleration is equal to final minus initial divided by t. Right, the final velocity is 15 meters per second, initial is 6, divided by the time, 20 seconds. Now if you punch this in your calculators, you're going to get 0.45 meters per second every second. Right, that's 1.3.1, 1.3.2. What are we looking for? The distance traveled. Right, as far as the distance traveled, you can simply use equations of motion as here as well. So I'm going to use this one. S is equal to the average velocity times time. Right, because at least with this one, it only encompasses quantities that have been given. Right, average velocity is u plus v divided by 2 times time. Now you substitute. Initial velocity is 6, final velocity is 15 divided by 2, the time 20 seconds. Right, now if you punch that in your calculators, we're going to get 210 meters. Right, now we look at 1.3.3. 1.3.3, calculate or determine the work done by the component of the gravitational force parallel to the plane. Right, we have two components of the weight. We have one that is perpendicular to the plane and one that is parallel with the plane. So they're looking for the work done due to this force. Right, work done due to the gravitational component parallel to the plane, which is equal to, now we know work done in general is force times distance. So the force here, because they're looking for the work done by the component of the gravitational force parallel to the plane, it means we use Fg parallel times S, right, which is the displacement. Right, this will be equal to Fg parallel is equal to mg sine theta times S. The mass is 5 kgs. G is 9.8 sine and theta is 25 degrees. Yes, so that's 25 degrees times the distance which you've just calculated, 210. Alright, so now if you punch that in your calculators, we are going to get 4348,742. This is in joules. Alright, pretty straightforward. 1.3.4, they want us to calculate the work done by the friction. Right, work done by the friction. Work done by the friction. Work done is force times distance or force times displacement. The work done they're looking for is the work done by the frictional force or work done by friction. Therefore, the force would be the frictional force times distance. The frictional force was 45 newtons. The distance, 210. Right? Now if you punch that in your calculators, we are going to get 9450 joules. Right, easy does it. Right, so once you are familiar with the concepts that I taught you on the lesson on Newton's laws of motion, as well as the one on work done, energy and power, the exercises become very easy. Right, 1.3.5. Now they want you to calculate the power exerted by the total force. Right, the power exerted by the total force. Right, 1.3.5. Now you can do this. Right, there's a couple of ways in which you can attempt this problem. One of which is if you first calculate the total force applied. Right, remember our vector sum of forces, which we determined or established based on our free body diagram. Right, we know F net is equal to this. Right, now from this is what we're looking for. Now F net we do not have at the moment, but we know from Newton's second law that F net is equal to ma. We have the mass and we have acceleration, so we can get F net. So from this point you make Ft the subject of the formula. Right, Ft is equal to, so you transpose this and that and they become positive. So F net plus Fg parallel plus Fr. This is F net is equal to, from Newton's second law of motion, ma, plus Fg parallel is Fg sine theta plus Fr. Now you substitute. Mass is 5 kgs. We calculated the acceleration, 1.3.1 is 0.45. So this is 0.45 plus the mass is 5 kgs. G is 9.8. Sine theta is 25. And Fr is 45. Right. Now if you punch that in your calculators, you should get the total force applied, which is 67.958 newtons. Right. Once you have your total force applied, now you can calculate, right, the power exerted by the total force, which is Ft times the average velocity. Right, so this will be Ft times, remember the average velocity here, because we're looking at initial and final, this will be u plus v divided by 2. Right, and then now you substitute. Ft is 67.958 times the average velocity, which is initial is 6, final is 15 divided by 2. Now if you punch this in your calculators, so this times this gives us 713.559 watts. Remember, power is in watts. Right, another way you can do this, now for this problem in particular, this is probably the easiest approach, or the much quicker approach. All approaches are easy, right? But this one would have, or is much quicker perhaps, or you can use this approach. Right, now we know that, right, from the free body diagram, F net is equal to this. Right, we know that F net is equal to this. Now if F net is equal to that, what it also tells us is that W net, so the net work done, is equal to total work done minus the work done due to the friction minus the work done due to the component parallel to the plane minus the work done due to friction. Right? So from this, you can calculate the total work done. Right? And use the total work done to calculate your power. Right? But before calculating the total work done, you would have to calculate your net work done. Right? Remember from the work energy theorem that the net work done is equal to the change in kinetic energy. Change in kinetic energy is half mv squared minus half mu squared. Right? So final kinetic energy minus initial kinetic energy. Now you substitute. This is half. Mass is 5 kgs. Final velocity is 15 meters per second squared minus half. Mass is 5 kgs. Initial is 6. And then if you punch that in your calculators, you get 472,5. This is in joules. Right? Now you have the net work done. We also have this and we have that. So we can get WT by making WT the subject. So WT, total work done, is equal to, then you transpose these two to that side. Right? So this will be work net plus work done to overcome, or work done due to the parallel components of the weight, plus work done due to friction. And here you have this plus, and you calculated that, and this is what we got. Right? Plus we also calculated this and we got that. Right? Now if you punch this in your calculators, you are going to get 14271,242 joules. Right? Then once you have the total work done, now you can calculate the power, right, exerted by the total force. Right? So remember that power is the rate at which work is done. Right? The rate at which work is done. So this will be equal to 14271,242 divided by the time, which was 20 seconds. Now if you punch this in your calculators, you get 713,562. This is in watts, which is essentially more or less the same what we got when we used this approach. Right? That is why it is important to be familiar with all the approaches, right? So you can use the one that is convenient for the problem you are looking at. Right? I hope you found this helpful. All right, so remember to subscribe if you want to see more content on engineering science. All right, and then of course like the video if you found this helpful. All right, see you in the next one, guys.